In data augmentation, usually some function is applied on the training samples to create the new ones, and based on the idea that the data augmentation uses, these new samples are created in different ways. Usually, invariances from the data are inspirations for designing inductive biases for data augmentations that can be used to further incorporate such invariances into models. And in the literature, the main focus has been to come up with new inductive biases for designing augmentations. And the causal factor for improvements from data augmentations has been mostly associated to these inductive biases. In this work, we would like to ask this question, whether there is another factor in this causal graph. To this end, let's have another look at how data augmentation is used. Usually when training a model, we go over the training data in several epochs, and in each epoch, a number of training samples has been randomly chosen and an augmentation function has been applied to create new augmented samples. After several training epochs, the model has seen the original training data for several times, as well as a set of augmented samples. Depending on the probability of augmentation used and the number of training epochs, the model often sees a number of augmented samples that are larger than the number of original training data. We will call this maximum randomness regime. We argue that there is another causal factor called randomness that affects the performance of methods using data augmentation. In order to evaluate the effect of randomness in different regimes, we introduce limited randomness regime, where the amount of non-augmented samples and augmented samples during training are equal. And this is done by augmenting every training sample only once, which results in a set of augmented samples with the cardinality equal to the number of training samples. We then compare the performance of models under maximum and limited randomness regimes to provide insights on the causal effects of randomness in data augmentation. We also provide complementary evaluation metrics to measure the alignment of inductive biases in data augmentation method with data and the task at hand. The first measure is approximate invariance error, and the second measure is known as augmentation worth. For these evaluations, we choose two tasks of image classification and audio classification, and we evaluate different data augmentation methods and datasets in each task. If you'd like to learn more about our work, come to our poster. Thank you.